In this video, we'll talk about I2C communication. I2C stands for Inter-Integrated Circuit, and it's a style of bus communication that is asynchronous and it's kind of similar to UART and SPI. It uses two wires, and what's unique is that they need pull-up resistors. Typically in the range of 1 to 10K. We'll talk about why that is necessary when the other typical digital communication protocols do not require them. So I2C is a bus, meaning that we can have, in the simple version, one master talking to several devices. And all I really need is common ground. The two wires are a clock called SCL and data SDA. So SCL goes to SCL and SDA goes to SDA. So what's unique here is that this is synchronous communication. Oh boy. Synchronous means that we have a clock. The clock line is controlled by the master, so when the master wants to talk, it starts pulsing the clock line. There's no chip select pin here, so both devices will hear that clock. So we must have some kind of method of saying, hey, device 1, I'm talking to you, I'm not talking to you, device number 2. There is the capability of there being a second master, and so how does one master control the clock as an output when the other is also trying to do it as an output? They have the ability to detect that there are two masters, and one will change its clock to being an input pin rather than an output pin, and the pull-up resistor is necessary for that switch to occur. Same thing is true for the data line. When the master wants to talk to the device, it makes its output pin, the data pin, an output, and the device makes its data pin an input. And when the device wants to talk back, they switch. So the master makes its data pin an input, and the device makes its data pin an output. And to help with that switch, it also gets a pull-up resistor. So the pull-up resistors mean that the bus, both wires, when there's no communication happening, should both read high. So that's one of the debugging things you can try is if you're looking at those two voltages and if they're both not high, that usually means there's some kind of problem on the I2C bus and the communication's not going to be working anymore. So this is 8-bit communication. So every write is going to be an unsigned char. How does the device know that you're talking to it? So when the master writes something, both devices will receive every single byte. Every device is programmed with an address. And that address has to be unique. So oftentimes the chips, let's say you have two of the exact same chip talking to a master on the I2C bus, they will have individual pins called A pins, like A0, and we'll make one 3.3 volts and another one ground, so that the address of this chip is settable using some pins. So usually some bits of the address are fixed and some bits are settable. So the address is 7 bits, some of which might be fixed and others might be settable. So the master, when it wants to talk, goes through a process of first doing a start bit, and then it will write 8 bits 3 times, usually, and then a stop bit. The first 8-bit write is the address. So both chips will see the start bit and the address. The chip that is not being addressed will then stop listening, and only the device with that address will continue to listen. The next byte is usually a command, like I would like to change this value of your memory, and then it'll send the value. So a start condition, specific chip, the address inside of the chip that you want to change, and then the value that you want to change it to. So that's a write. And then there's also the capability of reading from a chip. So that's a little bit more complicated. So we send a start bit. Then we send the 8-bit address. Then we send the 8-bit command, which is usually the address of some variable inside of the chip that we're going to change. Then we send a restart bit. Then we send the 8-bit address. Then we do a read that we usually call receive. Then we have to acknowledge that we got what we were looking for. Then we could repeat the process again if we wanted to receive more than one byte. And when we were done, we would send a stop bit. One more thing, how does the chip know that we're talking to it versus we're trying to read from it? So the address is 7 bits, but every write is an 8-bit. So the last bit of the address is either a 1 or a 0 to tell the chip that I'm either trying to talk to you or I'm trying to listen to you. So in the read, first we send the address with a write bit that says, hey, I'm telling you I want to read from this. I'll do a restart, and then I'm telling you I want to read, and then I'll do several reads. So the downside of this I2C communication is that if you're in the middle of one of these processes and the master gets reset, so the device might be in the middle of receiving one of these 8-bit commands, the master, which is the PIC, restarts and then starts a new start bit, the device doesn't know that that happened. So the device suddenly freezes and pulls down one of these lines. The PIC then freezes because it no longer detects that the pins are high by default, and then all the code just stops because there's a bus communication error. So when that happens, it's usually the best idea to reset the power to the whole board so that the device and the master start from scratch. Sometimes the devices have reset pins so that you can reset them in code. So you might have one more pin here connected to here so that when the master resets, it can tell this chip to reset. But that uses more pins, and we're trying to take advantage of the fact that we only need 2 wires here. And how many devices we can talk to? Well, a 7-bit address means we can talk to up to 128 different chips using just 2 wires. So that's pretty cool. Let's take a look at some of the code. So it's very helpful to have a library in this case. So I have an H file and a C file, and these ones are called no-int because they're not using an interrupt-based communication. So this is using a polling style method. We have an I2C setup function. That's where you can set your baud rate. We have the start and the restart bits. We have the send and the receive functions. We have, when you're receiving, you need to acknowledge that you got what you're reading. And then we have the stop bit. And you can take a look at what those registers are in the PIC. The important ones to look at would be the baud rate generator. Similar to SPI, we need to set the speed. Typical baud rates in I2C are 100 kilohertz and 400 kilohertz and 1 megabit, which are relatively low when you compare them to SPI. So SPI is a much faster communication, but uses more pins. The other thing I really want to point out here is that in the send function, or in actually all of these functions, there are while loops that say wait until the thing that you're trying to send or the thing you're trying to read occurs. In the send function, I've got a comment here that says if this bit is not on, or if this bit is on, that means that the thing you tried to send didn't go through. And I put an infinite while loop in here so that if you do try to talk to a chip and it doesn't respond back to you, it doesn't acknowledge that it received what you sent, the PIC just hangs. And so that is a good indicator that your communication needs to be power reset if the PIC freezes. So in our PIC code, we'll always try to have some kind of blinking LED going on, so that if you notice that the LED is not blinking, probably you got stuck at this infinite while loop, and the PIC is no longer able to communicate with the device due to the power reset. So those common baud rates, you'll look at the data sheet for the devices you're trying to talk to. 100 kilohertz, 400 kilohertz are by far the most common ones. Some will go faster. The downside to having some that are fast and some that are slow is that they all have to be on the same bus, talking the same speed. So we'll try to set most of ours to 400 kilohertz. So let's take a look at what this the voltages look like in Nscope. I've got the clock on channel 1 and the data on channel 2. And I'll need to zoom in to be able to see what these voltages look like. And I'll trigger on the clock. Stop it really fast. So we can see the clock is coming out. This first clock has the start bit, and then the next 8 pulses would be the data that is in this packet. Then the device is going to send an acknowledge bit back that says, I received those 8 bits, and the acknowledge, there should have been a delay in here so we can see is in here somewhere. And then the next transfer comes in another 8 bits, and then another 8 bits. And we'll slow down a little. And you can see that before the communication, after the communication, both of these pins idle at high. So this isn't something you can test without plugging your PIC into a device that talks I2C, because the PIC, when it writes to the chip, if that chip doesn't exist, will then hang here because it never gets the acknowledge bit. So you won't be able to test this until the next video when we'll use our first I2C chip.